Welcome to Easy Elim Learning Simplified. My name is Ruth, and today we are going to be looking at the topic chemical families, and our subtopic for today is chemical properties. So initially we discussed on the physical properties of halogens. So for today we will pick some chemical properties and discuss them, and later on we will finish that. So the first chemical property we'll discuss for halogen is that they're usually not that easy to form cations. So they have a very high ionization energy. You see they have 7 electrons in the outermost energy level. So it is easier for them to gain electrons than it is to lose electrons. So when you look at the ion formation of halogens, they usually form ions by gaining single electrons to form a stable configuration. So during the formation of this electron gain, energy is released. So initially we talked about ionization energy required. So we are absorbing that energy. But in this case, the process of gaining, we are releasing energy. So we usually call this process electron affinity. So when you look at the definition of electron affinity, it is the energy released when an atom in gaseous state gains an electron to form a negative ion. So if you have to compare it to ionization energy is the energy required. Electron affinity is the energy released. So when a gaseous atom gains in ionization energy, when a gaseous atom loses, and then to form a negative ion. So in ionization energy, it forms a positive ion. So you can see that difference. So this is also going to be a bit different from the trend in ionization energy that we saw in alkali and alkaline earth metals. For the electron affinity, it goes the opposite. So when you look at the trend of electron affinity, it decreases down the group. Why does it decrease down the group? So the size of the atom increases. So you look at the size of the atom is increasing as you move down the group to iodine. So when the size of the atom increases, it means the nuclear attraction or the force of attraction of electrons by the nucleus decreases as well. The farther it is away from the nucleus, the less it is attracted to the nucleus. So what happens is, if it is the outermost electron is attracted weakly by the nucleus, it means the ease in which the electrons are gained decreases. So you see, if you have a small atom and a bigger atom, this nucleus on the center can attract electrons very easily. As like for a bigger atom where the nucleus is it's so far away from the outermost electron, so it can't attract any electron that easily. That is what we mean. So down the group, the ease of attraction and the ease with which electrons are gained decreases. And the faster the ease of electron gain, the more energy is released, hence more electron affinity. So as you go down the group, there's less electron affinity. There's less energy that is released because there are less electrons that are attracted because the size is very small. The nucleus is so far away from the outermost electron, it cannot attract any electrons in comparison to the one that is so small. So as you can see about the ionization energy, for the four halogens is shown. So next, as you can see, the way the electron affinity is, you can see it's decreasing down the group. Next, we are going to look at some other chemical properties. That is the reaction with metals. So chlorine usually reacts with iron. You're going to see the reaction of these halogens with iron. So this is the setup. You can see chlorine is passed through a U tube that contains a drying agent, and then it's passed through another tube containing the iron, which is heated. So there's a reaction between our iron and the chlorine. The iron glows, of course, to form iron 3 chloride. And you can see there is another tube here containing solid J. We call this one calcium oxide. We are going to see the uses of this calcium oxide later, and then to the fume chamber, because we do not want the chlorine gas to go to the atmosphere. So the experiment should be done in a fume chamber. That's what we said, because chlorine is it's usually very dangerous and toxic, and then it's very poisonous and harmful to the body. And then the chlorine has to be dry. We want it to be dry before it reacts with the metal. So that's the reason why we pass it through the U-tube containing calcium chloride. So to prevent hydration, hence oxidation, which will then form iron 3 decahydrate. So we don't want that to happen, because the wet gas will cause this formation of this compound. The iron metal must be hot. We know the reactivity of iron is not that high, but if we heat it, it helps to form activation energy, which helps the reaction to start. And then anhydrous calcium chloride in the U-tube is used to dry chlorine gas, and in the pistol funnel is used to prevent water vapor from getting into the apparatus. So we can use it in solid J as well, but there is a better alternative, which is calcium oxide. It is preferred because it not only prevents atmospheric water to get into the flask, but it also absorbs excess chlorine. So it functions in two ways, and it helps preventing the chlorine from going to the atmosphere. And then some of the observations we noted in this experiment is that the iron metal glows red hot, and it forms fumes of iron 3 chloride, and then these fumes cool down to form a black solid of iron 3 chloride. It cannot be easily collected because it sublimes when heated. So this is a compound that can sublime. So you see the iron in the equation reacts with 3 molecules of chlorine gas to form iron 3 chloride. So in the conclusion, you see the iron 3 chloride sublimes when heated. That is the reason why it's not easy to collect it. Next, we look at aluminium. So aluminium also reacts with chlorine in a similar manner in the way that iron has reacted with chlorine. So aluminium reacts with chlorine to form aluminium 3 chloride, and also it can form aluminium. When you look at the second aluminium, it's actually a dimer compound. And then aluminium also sublimes on heating. You notice that when we come to period 3 elements as well, because aluminium is one of the elements. Magnesium also burns in a blinding flame when it reacts with chlorine, and it forms white fumes of magnesium chloride. So it cools to form a white powder, and that white powder is called magnesium chloride. So this is the equation. We repeated this equation when we were discussing alkaline earth metals and their reaction with chlorine. And then generally chlorine reacts with most metal when hot to form the corresponding chlorides. So you notice some chlorides forms two chlorides. Like in the case you are forming iron 2 and iron 3 chloride, the higher chloride is usually formed. So we do not form iron 2 chloride, but instead you form iron 3 chloride. Since iron 3 chloride is the most stable, so it's the one that is going to be formed. And then the reaction of bromine with iron. So you can see the setup below. So SAD soaked with bromine is heated, and then also it reacts with iron cool. So when you heat the bromine liquid, it changes into fumes, which react with iron. And then iron wool, when it's heated, it glows, and then it reacts with the bromine
fumes to form iron 3 bromide, we say that it's going always to form with the highest valence or valency or oxidation number. So that is the equation. Iron reacts with bromine to form iron 3 bromide. And you can see the product is red crystals of iron 3 bromide. When bromine reacts with zinc, it forms zinc bromide as well. And you can see also in the equation, so it forms zinc 2 bromide. That's the highest oxidation number. Bromine also can react with magnesium to form magnesium bromide, and this is the equation for the reaction. Bromine also can react with sodium in the same setup to form sodium bromide. So this is supposed to be sodium bromide. So this is the equation. And then iodine as well can react with metals. When iodine reacts with iron, as you can see, the iodine crystals are heated and also the iron hood is heated and the reaction occurs. So the purple vapor of iodine reacts with iron, and then the iron glows red hot and it forms the gray black crystals of iron 2 iodide. So that is the equation for the reaction. Reaction of iodine with zinc also, it reacts to form zinc iodide as you can see in the equation. And also iodine reacts with magnesium to form magnesium iodide as you can see in the equation. The same setup can be used to react iodine, it's supposed to be iodine, with uh, with sodium to form sodium iodide. So when you look at the reactivity of chlorine with metal, it's more vigorous than bromine, which is more vigorous than iodine. You notice we have been avoiding to use fluorine because fluorine is even higher than chlorine in the reactivity series. There is a small reactivity series for halogens, and fluorine is the highest. It reacts explosively with metal, so we avoid it as much as possible. So the reactivity of halogen decreases down the group, and you said that it decreases down the group because of the ease at which it's able to gain electrons. We said it gains electron easily when the atom is small. It's harder to gain an electron when the atom is bigger. So halogen reacts by gaining electrons. So the ease of gaining decreases in the group as the atomic size increases. We know that the distance between the outermost electrons and the positive nucleus becomes larger and larger as you go down the group. So it becomes harder to attract electrons as you go down the group. That is the reason why the reactivity of halogen decreases down the group. And you noted that this is different from alkali and alkaline earth metals, where the reactivity increases with the increase in the size of the atom. That is because in that situation they are losing electrons, so it is easier to lose as you go down the group. But in this situation, you are looking at gaining. It is easier to gain. The smaller the atom, the better it is for gaining. So as you go down the group, as the atom becomes bigger, it becomes hard and hard to attract electrons to itself. And then you look at finally displacement reactions. So when you look at the reactivity of halogens, the halogens that are more reactive can displace halogens that are in combined state of those in a low reactivity. So for example, test tube containing, you can see we have sodium chloride, bromide, and sodium iodide. You can see the halogens are in combined state. So they have reacted with sodium. So we are adding a few drops of chlorine water in each of them. And then we repeat the experiment with bromine water. So what we notice is if you use chlorine water, the yellow color of chlorine water fades in all test tube apart from sodium chloride. The reason why it doesn't change in sodium chloride because the ions that are there are similar, so it cannot displace itself. And then the colored solution is also formed. With bromine, the brown color only fades with the test tube containing sodium iodide, but it does not change in sodium chloride and sodium bromide. So when you look at what happens is that halogens displace each other from their solution. The one that is more electronegative or more reactive displaces the one that is less electronegative. When you talk about electronegativity, this is a tendency to attract electrons. So the one that is highly has a higher tendency of attracting electrons to itself, we say it is the most electronegative. And in halogens, fluorine is the most electronegative. When you go down the group to iodine, iodine is the less electronegative because it's very large, it doesn't attract electrons to itself very easily. So the one that is highly electronegative can displace the one that is less electronegative. So we didn't use fluorine because we said fluorine is very explosive. So for chlorine, I'll use chlorine instead. So chlorine can displace any solution containing bromide and iodide ions. So that's the reason why when we added the chlorine water, both the bromine and iodine was displaced from their solution. Bromine is more electronegative than iodide. That is the reason why it displaced it from solution. So example of equations that show this displacement. First of all, you can see in this reaction, we are reacting fluorine with sodium chloride. So what happens? Fluorine displaces chlorine from this reaction. So we form sodium fluoride and chlorine gas is given off. If we were to look at the ionic equation, you can see this is how ionic equation looks like. So the fluorine, which is in neutral atom, and the chloride reacts with chloride ion to form fluoride ion and chlorine gas. So fluorine basically has displaced sodium. If we look at, for example, chlorine, when it reacts with sodium chloride, with sodium bromide, this one is bromide, chlorine can actually displace this bromine to form sodium chloride and bromine gas is given off, just like you can see in the ionic equation. As for bromine with sodium iodide, you can see bromine can displace iodine and then it forms sodium bromide. It reacts now instead with sodium and then iodine is given off. So you notice in the observations, because chlorine gas is yellow, green yellow in color, that is what you are going to see. Bromine is brown in color, that's what you're going to see in the solution. And iodine is gray or purple in color. So that's what you're going to see at the end of the day. So that brings us to the end of the session. I hope you have been able to understand. In the next lesson, we are going to look at other chemical properties of halogens. So watch out for that. See you then.